Hello everyone, welcome back to another video of machine design. So we're going to be talking about this problem today. A steel rotating beam test specimen has an ultimate strength of 1,600 megapascals. Estimate the life of the specimen if it is tested at a completely reversed stress amplitude of 900 megapascals. According to Google, completely reversed stress refers to cyclic stress in engineering, where the stress fluctuates between equal positive tensile and negative compressive values, resulting in a mean stress of zero. This is a critical concept in fatigue analysis as it represents a loading scenario, such as the bending of a rotating shaft, that has a significant impact on a material's resistance to failure over time. Characteristics of completely reversed stress include zero mean stress. The stress oscillates around a central point of zero, meaning that there is no net or average tensile or compressive load. Equal stress amplitude. The maximum tensile stress and maximum compressive stress are equal in magnitude but opposite in direction. Stress ratio R of -1. In a fully reversed load, the stress ratio is defined as the minimum stress divided by the maximum stress. S min over S max is always -1. A common example is a rotating machine part, like a shaft, subjected to a constant bending load. As the shaft rotates, points on the surface experience alternating tensile and compressive stresses, leading to completely reversed loading. Significance in fatigue. Baseline for fatigue data. Fatigue testing is often performed under completely reversed stress conditions, producing SN stress life curves that define a material's fatigue strength as a stress ratio of -1. Effect on fatigue life. The presence of a non-zero mean stress, which is absent in completely reversed stress, can significantly reduce the fatigue life of a component. Therefore, completely reversed stress conditions provide a benchmark for understanding the inherent fatigue resistance of a material without the complicating factor of a mean stress component. Let's first take a look at some equations that we will need for this problem. So um, we will definitely need a figure 623, uh, which is a graph of like fatigue strength fraction F of ultimate strength at 10 to the power of 3 cycles for steels, with endurance limit equals to endurance limit prime equals 0.5, ultimate strength at 10 to the power of 6 cycles. Um, so And SE is the endurance limit. For completely reversed simple loading, we determine SE prime either from test data or we express it as an expression in terms of ultimate strength. For ultimate strength between less than or equal to 200 pounds per square inch or 1,400 megapascals, we can approximate SE prime by 0.5 ultimate strength. Um, and we will now also need to um, understand what mean stress and alternating stress is. So as you see over here, let me see if I can annotate. So over here, we have mean stress. And completely reversed loading, mean stress is equal to 0. And mean stress is sigma max minus plus sigma min over 2 because it is the mean. In completely reversed loading, we have that the mean stress is at 0. And this is sigma max and sigma min. Check for localized yielding. So we won't need all of these equations just yet, but we will need some of them. Start by writing what you know and what you do not know. So we know that the ultimate strength, SUT, is equal to 1,600 megapascals. And we know that the completely reversed stress is 900 megapascals. Um, and we want to find the F value because to calculate the number of cycles, or N, we are going to need to know the F value because from our equation sheet, N is equal to the completely reversed stress over A to the power of 1 over B. And these equations are not on the equation sheet, but they're very crucial to know. So you're going to have to put these on the equation sheet. So SF, or the fatigue strength, is equal to A times N to the power of B, where N is the number of cycles. Um, and from this equation, we have to know A. A is equal to the F times the ultimate strength altogether squared over the endurance limit. And B is equal to negative 1 over 3 log of F times SUT over SE, which is the endurance limit. So from here, we have to first find this value F. We already know our ultimate strength value, and we also have to find our value for SE. So we can find F from the table, and we can find SE also from our equation sheet. So first, let's approximate F. Here is figure 623. So we want to approximate F when the ultimate strength is 1,600. And if you know over here, 1,600 actually exceeds the scale of this diagram, unfortunately. So what we can do is we can extrapolate the data. We see that between 1,200 and 1,300, it's about 100. But ours is 1,600. So that is a difference of like 1,000, of like 300. So it'll be somewhere over here. So it'll be around 0.77 is what we can approximate it as. Around 0.77. So this is the value that we'll be using. So I'm gonna write about 0.77. What about our SE? We get that from our equation. From here, we see that for ultimate strength less than or equal to 1,400 megapascals, SE prime can be approximated by 0.5 times the ultimate strength. However, over here, our SUT is greater than 1,400 megapascals. So we will have to use SE prime is equal to is approximated. Well, these are all approximations of 700 megapascals. So that's what we will be using. Um, all right. So now we have all the needed information to solve for A and B. So A will be equal to 0.77 times the ultimate strength, which is 1,600 megapascals, and all together squared over SE prime, which is 700 megapascals. and A will be equal to 2168.32 megapascals. And B will be equal to negative 1/3 log of FSUT over SE. So plugging in known values, we have negative 1/3 log of 0.77 times 1600 megapascals over SE, which is 700 megapascals. Calculating this out gives us that B is equal to negative 0.0818 38. Yes. So that will be our value for B. And now from our equation at the beginning, we'll have that SF is equal to 2168.32 times n to the power of negative 0.081838. Now, what is the fatigue strength? It says that the life of the specimen, if it is tested at a completely reversed stress amplitude of 900 megapascals. So SF is actually equal to sigma AR for this problem. So it's equal to 900 megapascals. And thus we can solve for n by doing 900 divided by 2168.32. And we take the log of that. Or actually alternatively, we don't have to be that complicated. We can multiply it by the power of negative 1 over 0.081838. And this will give us n. So n is equal to 46,377 cycles, or about 46,400 cycles. I will link this book in the comments below, but basically this is what we are using, the high cycle SN line. So equation 612 can be solved for life in cycles corresponding to completely reversed stress, replacing the fatigue strength with completely reversed stress. And the typical SN diagram is only applicable for completely reversed loading. For general fluctuating loading situations, the effect of mean stress must be accounted for. In section 11, this will lead to an equivalent completely reversed stress. That is, so keep in mind that this replacing SF, the fatigue strength, with completely reversed strength, sigma AR is only for completely reversed stress cases. Thank you for watching this video, and I hope that helped you. And let me know in the comments what you guys think. See you later.